Thank you for the invitation. The failed rift that you see on this map is a 1.1 billion year old one. Its northern boundary today is near the United States-Canada border. It outcrops near Lake Superior, one of the world's great water fresh lakes, and it extends very far south on either side to the edge of what must have been the edge of the Laurentian continent then. Laurentia is the name for the assembled part of North America in the Precambrian. The name of this rift is the Midcontinent Rift, which is an awkward name, but nevertheless, it is the Midcontinent Rift in North America. North America's craton Laurentia has seen over 2 billion years of geologic history, and there are three major rifts that I'm showing you in this figure: the Midcontinent Rift, the Southern Oklahoma Alocogen, and the Reelfoot Rift. These three rifts have very similar tectonic history, widths as shown in the gravity signature architecture, a sort of similar evolutionary path with extension and then magmatism, subsidence, and rift inversion by compression, by collisions of continents and plates with Laurentia. But there are differences in the processes. And studying failed rifts gives us insight into final stages of continental rifting, passive margin formation, and early stages of seafloor spreading. One of the questions that I frequently get when I give talks about the Midcontinent Rift is, how is it related to the Reelfoot Rift? And the answer is they're not. They're about 500 million years apart. The Midcontinent Rift formed, we think, when Amazonia rifted away from North America 1.1 billion years ago. The Reelfoot Rift and the Southern Oklahoma Alocogen were part of the rifting that formed the Iapetus Ocean. In this case here, a small terrain rifted away with the leftover failed rifts, and this small terrain is now part of the Argentine Precordillera. The apparent polar wander paths for Laurentia have big cusps or churns in them during the time of the Midcontinent Rift formation, and then much later on, the Reelfoot Rift and the Southern Oklahoma Alocogen. Getting back to the MCR, to the failed 1.1 billion year old rift, it outcrops in the Lake Superior area, so people can actually study it with boots on the ground. But for most of its 3,000 kilometer length, it's buried under a whole bunch of sediment. However, it contains a lot of dense and highly magnetized volcanic rock, and therefore the buried part shows up very nicely with gravity and magnetic surveys. In fact, starting in the 1940s and 50s, people who looked saw large anomalies in these areas and realized that it was part of the feature that was visible in the Lake Superior area. There are more than 2 million cubic kilometers of igneous rock fill, and it's a great example of a magma-rich rift that failed to evolve to full seafloor spreading. We'll look very briefly at some questions. Is it a rift or a large igneous province? How did it form, evolve, and implications for continental rifting and passive margins? There's big debate in the past if it was a rift or a lip, and the answer is yes. Continental rifts are linear segmented depressions filled with mainly sediment, but some igneous rock that form by extension and may become a passive margin. Lips are usually huge volumes of continental flood basalts associated often with hot spots or some sort of deeper mantle upwelling. The Midcontinent Rift is different from the other continental flood basalts in that the average thickness, when you plot area versus volume, for many of these is about 1 kilometer. But the Midcontinent Rift average thickness is between 5 and 10 kilometers, because most of it was deposited in a subsiding trough. And these thicknesses are suggestive of the magma accumulations at magma-rich passive margins. How did it evolve? We're very lucky that in the 1980s, there was very high quality seismic reflection data taken across Lake Superior. This shows the profile of this figure up here from the GLIMPSE program, and a lot of data from onshore to put together information that we used to figure out how it evolved. Before we get into how it evolved, let me just take you on a brief geology tour. There's up to about 20 kilometers of igneous rock, mainly flood basalts, especially Lake Superior. Above it are up to about 8 kilometers of sediments, that is post-rift extension sediments. One of the intriguing things for the older volcanic rocks is that they truncate towards the edge of this basin, indicating deposition on this side with an active normal fault, active extension going on. And in fact, across where we have data across Lake Superior and the areas, especially to the west, we see that they're alternating half grabens with a major normal fault on one side and then the next package on the other, like we see in many rifts today. The upper volcanics and the sediments above it dip from both sides and thicken towards the basin center, indicating deposition in a subsiding but not extending basin. There have been great debates of whether or not this syncline structure arose either from basin subsidence or from later compression and inversion with the subsequent continent collisions to North America. And the answer is that it's the former basin subsidence. So in order first to get this huge accumulation of volcanic rock, we needed to have the rift there and the weaker crust to begin with, so the volcanics could accumulate in it. So at least 10 million years before the beginning of the massive continental flood basalts at 1109 MA, we had extension or what we might call passive rifting. Then there was a period of about maybe 15 odd million years where we had active extension, but we also had the continental flood basalts filling this half graben. Then the extension ended, but we continued for another about 10 million years to have continental flood basalts. And then the volcanism ended. We had continued subsidence and sediment infilling the basin. Much later, there were a series of collisional events for North America that inverted and uplifted the rift. The original normal fault became a reverse fault. New reverse faults formed on the other side of the graben and resulted in uplift and erosion, in this case in Lake Superior, exposing some of the basalt at the surface today. So what we see around the whole Midcontinent rift, the final thicknesses and the shape and a lot of other factors depend on varying amounts of extension, volcanism associated with the rifting, compression, and the usual factors for rifts. What's unusual with the Midcontinent rift is that most of it has a gravity high. This is unusual for rifts because most rifts have gravity lows. This is a figure from the Rio Grande Rift in the United States to the west of the Midcontinent rift that's actively but slowly extending today. Most rifts have gravity lows because they're filled with largely sediment. One of the questions is, how did we end up with this gravity high? How much of it is due to just the igneous rock itself, and how much later to the inversion? Initially, after the extension stopped, there was a large amount of volcanic rock near the surface. There would have been a gravity high. With the Sag Basin and a large amount of sediment covering the basalt, we probably would, if we could have come back 1 billion years ago, we would have measured a gravity low. And now with the inversion, there's a gravity high because of the uplift of the basin and the basalts being so close or at the surface. The Midcontinent Rift is a lot like the East African Rift today. The East African Rift has a triple junction. We have Arabia moving away from Africa with mostly seafloor spreading in the Red Sea, or half and half, seafloor spreading in the Gulf of Aden. And we have two major plates, Nubia and Somalia, and a few microplates thrown in the boundary. What I've done here is I've turned North America upside down. Canada is at the bottom, the United States at the top, the Great Lakes here with Lake Superior, where the Midcontinent Rift outcrops over here. And we would have had a triple junction with Amazonia rifting away from Laurentia or North America. And the Midcontinent Rift is this failed third arm, now failed, the way the East African Rift today is, of course, presently extending, but if it doesn't succeed, it will become a failed rift. At the time of the active extension for the Midcontinent Rift, the Illinois microplate was moving away from the rest of Laurentia. And the rift failed. It didn't succeed and become a passive margin on both sides. And so the Illinois microplate was reincorporated within Laurentia. This is kind of similar to what we've seen from some recent work we've been doing with the Burke and Dewey papers about three-arm junctions and how continental rifting starts, where in their model you connect up the high areas with the three-arm junctions. Two of the arms become the new plate spreading boundary, and the third a failed rift or an allocogen. But what we're seeing is that these allocogens are actually part of microplates that are formed that are active during extension, and that when seafloor spreading is successful, the failed microplates become part, and their boundaries get reincorporated between with the larger plates on either side, the way what might happen to the microplates now in the East African Rift, that they'll end up, if the rift is successful, they'll end up either as part of Somalia or Nubia. Midcontinent rifts, the margins look a lot like what the MCR might have evolved to had it been successful and started seafloor spreading. At a volcanic passive margin, you have seaward dipping reflectors with large gravity and magnetic anomalies. Beneath it, you have the high velocity lower crust, the underplate at the Moho, with a lot of the magma that never made it up into the overlying crust and the surface. For the Midcontinent Rift, we can see around the shores of Lake Superior these dipping volcanic packages. So these are really seaward dipping reflectors you can walk on, whereas now at most rifted passive margins, they're all covered with sediment. So much of the margin structure that we see is inherited from rifting. So just again, we have the seaward dipping reflectors that in the case of the MCR never got there, but they're these volcanic layers. We have a high velocity lower crust due to the residuum or underplate or rift pillow that where the magma never makes it up into the crust or the surface. And we do, although it's not shown here, have that imaged beneath the Midcontinent Rift.
Carol, you have 1 minute left, okay?
This last slide and then conclusions. So when we have volcanic passive margins today, The ratio between the SDRs and the high velocity lower crust is about 0.3. For some reason, the Midcontinent Rift, that ratio is about 1 to 1.5, and we're not sure why it's so different than the evolved successful passive margins. So in conclusion, the MCR formed and evolved in a plate tectonics context consistent with what we know about plate tectonics then and younger continental rifting events today. It began as a continental rift and subsequently became a lip. The volcanism and extension ended long before the compression began. The Midcontinent Rift gives insights into how volcanic passive margins form. And the bottom line is that rifting processes 1.1 billion years ago operated a lot like today's. Thank you.
Thanks a lot, Karen. There's time for 3 questions. Gianreto, you have the first one on underplates. Did the last slide answer your question already?
Yeah, I was just, at the end you came to the underplates, because in the first slides you did not show the underplates. You had a lot of extrusive material, and it was the brown underneath that was the continental crust. So I was wondering why that you did not put the underplates from the beginning.
That particular profile seismic reflection image did not image the underplate area. There are a couple or one other major glimpse profiles that did, and wasn't included. That they were mainly interested in kind of oil and gas at the time, so they weren't really trying to image that deep.
But do you think that there are underplates or that they are not? And because if there would not be underplates, you would have to have very ultramafic magmas.
The underplates have been imaged everywhere there's data to do it, including some recent tomography data that have been imaged for the West Arm too. So it's definitely there. It just wasn't imaged in that particular profile because there wasn't enough energy to get down below the crust.
Okay, thank you very much.
I have one question that I can ask because there's another question, but I wanted to ask it anyway. So you have 20 kilometers of volcanics there, and that must have, all this melt must have gone through the lithosphere. It must have weakened the lithosphere tremendously. So in your scheme, in the end, when you say this is the third arm of a competing other rift system, that means that the other rift, the one towards Amazonia, must have been even weaker. And I find that interesting because usually over the last few 100 million years, whenever there was a plume and a rift at the same time, and there was competition between different rift arms, then usually the one with the plume won because we believe that it weakened the rift so much that that became the weakest branch. But here it seems to be different. What do we know about the other rift branch? How weak must that have been?
We don't know very much about it. There's a little part of Amazonia where they've recently dated volcanic rocks that start like 2 million years before the voluminous stuff in Lake Superior. One of the interesting things about it is that at the time this rift was forming, North America was moving south very rapidly. So there are a lot of questions about how a massive upwelling area could have remained beneath North America. It's kind of a different situation than Africa being largely stationary. So we don't know very much, that's really the only thing we know. And one of the other issues is that because of the subsequent collisions with the Grenville, with the magma formation of Rodinia, and then rifting, we really have very little data about what the Amazonia margin would have looked like.
Okay, thank you.